Okay, Physics 30s, back again here. Page 56. Let's do some of these practice questions together so we get a good understanding of this. So we're looking at the rules, right? Number 3, magnetic force on a wire. I call it the third hand rule for force because there's a force involved in a current carrying wire in a magnetic field. Okay, both A and B we're going to do. Determine the direction of the magnetic force on the wire. So the same kind of idea, right? You got your north to south, that's going to be your magnetic field. The electron's going up, and so my hand's going to be oriented like this. Okay? And so, of course, you can see that it's going to be out of the page once again because the magnetic field goes that way, electrons are moving upwards, and so it must be out of the page. Okay? The external magnetic field for this one. So what does this look like? Well, here's what you do, right? You essentially are going to point your thumb to the right on your left hand, okay? Point your palm down, and so, of course, the external magnetic field must be into the page here, okay? Must be here and here. You can do this in a few different spots if you want to emphasize the fact that it must be in. Okay? Take a look at this part C. Electron flow. All right, magnetic field is going into the page, so point your fingers into the page. Use your left hand. Point your palm over to the right, and therefore the current must be going upwards. Okay? Now the last part, electron flow here. So you have the north to south, your magnetic field goes like this. Okay? And the magnetic force goes that way, and so what we have to have is the current going into the page. Okay? Electron current. Moving along here. The conceptual understanding is key, okay? So a decimal 350 Newton wire is placed into a decimal 6 Tesla magnetic field as shown. Length of the wire 7 centimeters inside the field. What are the magnitude and direction of the electron flow to keep the wire suspended? Okay, so what do we have here? Well, same kind of idea. We have the magnetic force is equal to the gravitational force. Now here I'm not going to use the absolute values. I don't have much room anyways. And I know that there is the weight of the wire already given, so I already have Fg. Fg is right here, okay? That's given. Now I want to know the direction and magnitude of the electron flow. Well, let's figure out the magnitude first. And so I have L perpendicular, I, B is equal to Fg. Now I'm just going to go ahead and solve it for the current, okay? So I is equal to Fg over L perpendicular and B. Let's put in our stuff here. 0.350 over 7 centimeters, so 7e negative 2. And the magnetic field, decimal 6. Sorry, I'm running out of space, so I'm just doing it like this, okay? All right, calculator time. I got 8.33. And in this case, it'd be amperes. Now, what about the direction of the flow? Well, what we need to do here is we need to think about how we're going to set up our hand, right? We got north to south, so that our fingers are going to point towards the south pole. In the case of the wire being suspended, we want to make sure that the magnetic force has got to go upwards. Okay? And then the B field goes this direction. And so to set that up, of course, you're going to realize that you have to have the current go in. Okay? So electron flow is going to be into the page. All right, which of the following is equivalent to unit for the Tesla? Very common question. So when you want to solve for B in the formula, then you have the following. You have Fm over I, L perpendicular. And so what do you have here for force? Well, you have newtons. I, you have amperes. L, you have meters. And so it looks kind of like this, okay? Just going to get myself a little bit of space here. You have newtons over amps Now an amp is a coulomb per second, so this should be a Newton over coulombs per second times meters, which is a Newton times second over a coulomb times a meter. Do we have one of those somewhere on this? Yeah, we do. It's part B. All right, question number 4. A 13-centimeter long wire experiences a magnetic force of .620 newtons. If the perpendicular magnetic field has a strength of 1.5 teslas, then determine how much charge flows through the wire in 4 minutes. Okay. So we have the whole idea of the force here already given. So what we should do is we should go ahead and calculate I in the formula. So Fm equals L perpendicular, LP, L perpendicular, IB. Let's solve it for I. I is equal to Fm over L perpendicular and B. Let's put in our information here. 0.620. L is 13 centimeters. So 13.0 E negative 2. And the magnetic field strength, 1.5. All right, do the calculation, please. .1795 amperes. How much charge through the wire flows through the wire in 4 minutes? So what we have here is I equals Q over T. We want Q is I times T. So 3.1795 amps multiplied by 4 minutes times 60 seconds in a minute. We still want to keep 3 sig digs though, okay? 763 coulombs. All right, we'll stop it right there.